Welcome back to our discussion of section 2.1, which is really our inspiration for everything we're going to do for the rest of the course. Okay. And we've been talking about this idea of the average rate of change. Okay. And just to remind you, if we've got some function like this, and we've got two inputs, say the input A and the input B of this function, then we've said, okay, even though this function is very much not a line, I can connect these 2 points with a line. Okay, and what are these 2 points? They're A f of A and B f of B. And even though this function is very much not a line, I can make sense of the idea of the slope of the function f between A and B, at least on average. And we call that the average rate of change. And it's just the slope of this blue line, which I'll remind you we call the secant line. So to spell it out, what is the average rate of change of f on AB? This is how I write the interval from A to B, by the way. If I'm trying to be concise, I'll just use the brackets here. So what is the average rate of change? It's the slope of this line, which happens to be f of B minus f of A divided by B minus A. Or, the way I phrased it last time, this is the change in the output from A to B. This is the change in the input from A to B. Now, I want to point out, we don't need to have some sort of deep world-shattering problem to apply this to. We can apply this definition just to any function at all. So I'll go ahead and in this video, we're going to talk a lot about applying this idea to our favorite function x squared. And I'm going to mark off 2 points here, one of which is going to be minus 1, 1, and one of which is going to be 416. And I'm going to go ahead and draw the secant line here between these 2 points. Okay, so this is our function x squared, and this secant line is how we would go about understanding the change in f from an input of minus 1 to an input of 4. Namely, we could just go ahead and calculate the average rate of change of this particular f of x on minus 1, 4, and we'll get that it is 16 minus 1 divided by 4 minus minus 1, which is 15 over 5, which is 3. Okay, so in other words, what we've just calculated is that this line here between these 2 points is slope 3. And so on average between these 2 points, the output is going up by 3 for every 1 the input goes up. But this seems to not really capture what's going on here. Okay. In fact, actually, if you look at it, even though on average the function is getting bigger in output, originally it doesn't even do that. It actually originally gets smaller. And then to make up for the fact that it gets smaller and then goes slow for a while, it has to speed up. And so you could probably even make sense if I asked you the question, at the point 4, is the function growing faster, slower, or at about the same rate as the average over this interval? And I think, sort of intuitively, you can make sense of the fact that it looks like here at 4, the function is much steeper. That is, this black graph looks much steeper than this blue line. And so I want to be able to make a statement like this. Namely, I want to be able to say the slope of the graph at this point is steeper than the slope of the blue line. That is steeper than the average rate of change. And if I tried to put a number on it, I'd say something like is more than 3, because the blue line has slope 3. I think the slope at this point is more than 3. That's basically what my intuition tells me. And now we come to what all of calculus is about. Because what did I say? The slope of the graph at 4. And although so far we've figured out how to make sense of the idea of the slope of a graph between 2 points using the average rate of change, we haven't yet figured out how to make sense of the slope of the graph at a point. And this, figuring out how to make sense of the slope of a graph at a point, is what stuck mathematicians up until the 1600s when calculus was discovered. So even though there's this intuitive idea of the slope of a graph at a point, people weren't able to really make sense of it until the 1600s. And we, in this course, are going to learn how we make sense of that. So to distinguish from the notion of the average rate of change that we've been talking about, when we want to talk about the rate of change of the graph at a specific point, or the slope of the graph at a specific point, we're going to use the term instantaneous rate of change. So instantaneous rate of change, that's at a point, versus average rate of change, that's over an interval. Now, if I just go back and show you this picture, and I remind you that the only thing that has a slope is a line, can you picture a way to draw in a line here at 4, which has a slope that I would want to call the slope of the graph at 4? And if you squint at this, it might take a bit of squinting, you might start to see something. Namely, you might start to see a line that looks very much like this, where I've sort of, and I'm maybe not going to take these words too seriously, but I've drawn in a line that goes the same direction as the graph at that point. So I've tried to sort of draw in a single line in red that captures the direction of the black graph at 4. Now this idea, the idea of drawing in a line that sort of captures the direction of the graph at a point, this is called the tangent line. And we're going to be talking a lot about tangent lines as we continue in this course. Okay, so again, the average rate of change is the slope of a secant line. The instantaneous rate of change is the slope of a tangent line. So what remains to do? I want to convince you, by the end of this video, that the slope of this line, the tangent line that we kind of imagined drawing in here, I want to convince you the slope of this line is 8. The slope of this blue line was 3. And the slope of the red line, I'm going to try and convince you is 8. That is, I'm going to try and convince you that we can really make sense of this idea of a tangent line. So how am I going to convince you that the slope of this line is 8? What I'm going to do is I'm going to make a table, and the first entry in my table is going to be the slope of this line. So here's my table. Slope of secant line through a squared and 4/16. Okay, that's what I want to write down. Okay, so I'll have what point I was at here, and then I'll have the slope here. So this blue line in the picture, that is the secant line from -1, 1 to 4, 16. So here I'll write -1, 1. And here I'll write the slope of that line, which we've calculated is 3. So what am I going to do next? I'm going to draw in another secant line. This time, I'm going to start here instead. So this is 0, 0. And I will draw in that secant line. And it's not so hard to see the slope of this line is 4. Next up, I'll go up here to 1, 1. And I'll draw in this secant line. And so this is the line from 1, 1 to 4, 16. So it has slope 15 over 3, which is 5. And all I'm doing here is writing down a list of points, and it's a pretty natural list of points, -1, 1, 0, 0, 1, 1, and the slope of the line that connects that point to 4, 16. So next up, maybe I come up here to 2, 4. I draw in this line connecting there. Okay, and so the slope of the line, again, from 2, 4 to 4, 16, will be 16 minus 4, which is 12, divided by 4 minus 2, which is 2, 12 over 2. That means this green line, it has slope 6. And so here we go 2, 4, so slope 6. Now, it's not so hard to see a pattern here. I keep moving over by 1 from -1 to 0 to 1 to 2, and the slope keeps going up by 1 from 3 to 4 to 5 to 6. And so probably without even going back to the graph, I can probably guess, okay, this is going to be 3, 9, and that's going to be 7. And then I sort of know, well, okay, well, it's next. The next thing is going to be 4, 16, and 8. But here is the gotcha moment. Because what is this line purporting to be? This line is purporting to be the slope of the secant line through 4, 16, and 4, 16. And that is very weird because, well, this is the same point, so there is no sense of what the slope through here is. But somehow the universe knows that this really means the tangent line. That is, the line that I drew in red to start with here at this point. And so we can actually find the slope of this tangent line by looking at the slope of these secant lines and sort of finding the pattern and filling this in to fit the pattern. So again, this was slope 3, 4, 5, 6, and then there was one in here with 7, and then this is 8. Okay, and so that tells me this. This is the mystery that mathematicians had to contend with as they tried to figure out calculus. How exactly is it that I'm making sense of this idea of the slope of the line through this one point in the direction of the graph? We have this sense that the universe knows the answer is supposed to be 8, but where is that 8 really coming from? Now, in this one specific instance, that is in the case of the function being x squared, I can show you that this 8 did not fall out of nothing. There's a way we could do this. Namely, in this table, again, all of these points look like an input a and then the output a squared. Again, that's just because the graph we were looking at was y equals x squared. So when this is a squared. I can write a formula for this slope. Namely, this slope is 16 minus a squared divided by 4 minus a. Okay. That's just the slope through this point and that point. And so if you want to check, if I plug in minus 1, 1, then I get 15 over 5, which is 3. If I plug in 3 for a, then I get 16 minus 9, which is 7, divided by 4 minus 3, which is 1, so I get 7. Hooray, all of this works. Okay. If I plug in 4 for a, then I don't get 8. If we were to plug in 4, what would we get? We would get 0 over 0, which is undefined, which is thoroughly unhelpful. But I want to make one observation here, which is that if I actually look at this 16 minus a squared divided by 4 minus a, that actually factors, because this is a difference of squares, as 4 minus a times 4 plus a divided by 4 minus a. And now my 4 minus a's cancel, and I am left with 4 plus a. And now, if I plug in a equals 4, what happens? By miracle, I get 8. What we're trying to do in Chapter 2 is to generalize this process. That is, we want to figure out a way to go from some graph like this, or some quantity like this, and we want to figure out how to make sense of plugging in the value of an input where this thing doesn't actually work. And in so doing, we're going to learn the tools we need in order to talk about tangent lines and eventually what we're going to call derivatives. So that's a preview of what is to come in Chapter 2. I'm going to do one more video of examples involving average rate of change, just so that you will be prepared to do the homework, and then we'll pick up with the rest of Chapter 2. But that's all for this video. I'll see you next time.